Hello and welcome back. In this video I want to go over something that I feel gets a little overlooked on the Siemens control, and that is variable arrays. An array is very similar to a standalone variable where it has a data type and it has a naming convention and it holds a value. What I want to explain to you in this video is that variables and arrays, while similar, are very different as far as their core structure is concerned. So if you're not familiar with variables, I'll do a quick overview as to what variables are and the data types that they consist of. So a variable is basically just a storage container for data. That data can be in the form of an integer, which is a signed value, either positive or negative, and it's a whole number, so whole number 1, 2, 3, 4, no decimal places. It could be a real number, which is a decimal number, also signed. It can be positive or negative, 1.1, 2.2, 3.333, 4.125. It can be a Boolean, which is either a true or a false. It can be a char, which is an ASCII character. It is a single letter character, A, B, C, something like that. It can be a string, which is basically just a group of characters put together. A word is a string, so the word bus or the word Siemens or the word array are all strings in the world of computers. We can also identify our variable data type as an axis or a frame. The ones I want to go over today are going to be integers, real values, and strings, because those are the ones that are most widely used when you're dealing with variable programming and things like that. For anybody familiar with variable programming, we know that under our offset table in our R variables, we have this table that starts off at R0 and can go up. In this case, we're going to R999. So we have 1,000 variables that we can store for our program needs. Now, our variables are similar in fashion to what an array will do, because in this case we have R0, R1, R2, R3, R4, so on and so forth, and the R is going to be the name of the variable, so to speak, and then 0 through 999 is going to be the value of the R variable. So now if I go to MDI and I type in something like R0 equals 1.12345, terminate that with an M30, hit cycle start. If I go to my variables page under offset user variables, we can see that R0 equals 1.12345. I'll go back and I'll say R0 equals 5.4375, something like that. Go back in and we can see that the value changes. From there I could say something like R1 equals R0 divided by 2, cycle start, and we'll see that we have this value here. If I make that a 0 because it was very close to the one that was in there, cycle start, and we can see that there it is again. So we could do the same thing with arrays, but the thing with arrays is that we're not limited to just R variables, and we're not limited to just numbers. So to show you that, in MDI, I could say def int for integer. We'll just call it array1, and I'll say that it contains a value of 10 inside of the square box. Now, what this does, I'll show you when I hit cycle start. I'll stop this with an M0 so I don't lose my definition. When I hit cycle start and I go to my offset page, if I go into my local LUDs, you'll see that I have an array table of 10 values. So I'm sure you could see where I'm going with this. I defined one integer value, I gave it a name called array1, and I gave it inside of here a value of 10, which creates 10 instances of the variable array1. Could change that, make it 100. Cycle start, go back to here, and we can see that our data table has changed. Now we have 100 variables called array1. We'll bump that up even further, and I'll say that there's 1,000 of them. So now we have array1, value 0, all the way down to value 999. So we have 1,000 instances of this array1 variable that we can utilize within our program. So when you define an array, you define it with the value. So we could say that in this case we'll do a real. You give it a name and you make it something that is relevant to your program. And a nice thing that this would be used for would be probe points. If you wanted to capture the z value in multiple points of a part. So we could say probe point, and then inside of here we could say 20. When I hit cycle start, go to my table, we can see that we now have variables called probe point 0 through probe point 19. Arrays always start at a data register of 0, and this is common for a lot of programming languages as well. C, C++, Python, they all start with an array point of 0. And from there, they progressively go up from 0 through however many data points you tell the array that it contains. So I'll go a little deeper with this, and I'll create an integer array called int array with a value of 30. I'll create a string, and inside of the string, I'll say def string, and then I'll say a string of a maximum of 20 characters. And then inside of there, I could say string array with a value of 20. And then I'll do a def bool, and I'll do a bool array of 10. And when I hit cycle start, I'm locked in at the M0. If I go to my offset page, we can see here that I have the original 20 probe points. I have 30 integer arrays. I have 20 string arrays that will hold a maximum of 20 characters. So if I put in too many characters, you can see that it says invalid character, because it ran out of data space that it can hold. And then inside a bool array, I have now 10 Boolean variables that I can use to assign true or false values to within my program. Now the nice thing about these arrays is that they are independent variables. So the data container of array register 0 has no bearing on the data container of array register 10. They are two standalone values that can be used to manipulate data within your program. Again, much like the user variables here, but the downside to these user variables is that you only have 1,000 of them, and they're only decimal values. So you can define as many variables as you need inside of your program, and then instead of having to remember all of your R variables, what number each one contains what value, you would have a clearer description. So in this case, if I wanted to access my probe points, I know that my variables are going to be called probe point, and then it's just a matter of accessing the array value for that data. Doing it this way will only create a local variable, and again, it's a volatile variable, so every time you run your program, these variables will create, the variables will populate, and then when the program is done, they will terminate and they will disappear forever. If you want something a little bit more robust, what you would do is you would create a user variable table by going to menu select, setup, system data. Under NC data definitions, you can create a new GUD table called GUD4, 5, 6, 7, MGUD, SGUD. In my case, I created one called UGUD. Now these are all names that are predefined. So I created a table called UGood. And inside of this UGood, you can see I have a bunch of definitions inside of here to define different variable types, but these are all commented out. I have one in here that's not commented out called def nck real work offsets. And what this does is you'll see that there are two values inside of the box. And what this does, this creates a two-dimensional array. And we'll get into that later on in the video. But you can create this ugud.def file. And if I were to remove the comments of all of these, close this out, reinitialize the UGood table. If we wait for a second, the table gets initialized. It gives you a message that states that the activation has been completed successfully. If you do not get this message and you get an error, please go back in and change whatever could be going wrong inside of here, because if you don't and you try to reload the software, you will lose some important data. The control itself has a tendency to want to crash in a situation where it's missing one of these definition files. So be very careful with these. That being said, if I go to my offset page and I go to my global GUDs, we can see inside of my Gud table up here that I have a variable called first number, second number, and result number. These are just standard variables. Underneath that, I have this array structure here called hey there. And these are a multi-dimensional array type, square bracket, and then the number is separated by a comma. These become what they call a multi-dimensional array. It's not as scary as you will think, but you see that I've created damn near a bazillion values. I then have some variables called tool length x, tool length y, tool name, tool num, probe point, min point, some standard values for string storage, some standard variables here for some real values, and then under here I've got this work offsets that again goes up to 50 points and 5 points of two-dimensional array. So you can see that, I mean, there's tons and tons and tons of data storage now that I have access to, and this is non-volatile. So these values will get stored and they will remain stored until they get changed or until they get deleted. So that's a way that you can create data arrays and store your non-volatile information. So now you never have to go into your R variables and start using up all of those. On some controls, they're limited to 100 R variables or 200 R variables. I just happen to have 1,000 in my instance of Sinutrain. I can also manipulate this data with R variables. So I'm not limited to just using my LUDs, my GUDs. I can say something like R0 is equal to 1.1, and then I can say probe point square 0 is equal to R0. When I hit cycle start, I get an error message, and that is because I have the probe points established in the Gud table, and I have probe point established here. So it's just creating a data conflict. So I'll just create def real probe points, and then I'll say something like probe points 0 equals R0, cycle start. And then when I go into my offset page, I have R0 is equal to 1.1. And when I go to my local LUDs, I'll see that probe points, square bracket, value 0 is also equal to 1.1. So I can interact with these variables via the R variables. So for data storage that you don't want to have to go in and find it in the local table or in the global table, if you just want to store the values back to R variables, at that point you can. So here's where it gets a little bit tricky. Now arrays are, again, storage containers for bits of data. If I just comment these out and I say my def real probe point, I want to give that a comma and another 20. When I hit cycle start and I go to my offset page, local LUDs, you'll see now I get probe point 0, 0, probe point 0, 1 through to 0, 19. Then I get another set of probe points called 1, 0, 1, 1, 1, 2, all the way down to, again, 20 points or 19 because of the 0 being the first register. Then I get probe points 2, 0, 2, 1, 2, 2. So what I've created essentially is a two-dimensional array, and this is easier to think about looking at an Excel spreadsheet. An Excel spreadsheet has rows and it has columns. So we could look at this like 0, 0, 0, 1, 0, 2, 0, 3. And then we could look at this as 1, 0, 1, 1, 1, 2, 1, 3. And we could look at this as 2, 0, 2, 1, 2, 2, 2, 3. So we have rows, we have columns, and we can think about it in a spreadsheet type form to make it easier for us to visualize how we're storing this data. So each of these cells here will contain a numeric value, and each of those values will be, in our case, we could say 1.1, 1.2345, 2.5432, and whatever. So we're not actually storing the row and column values, we're storing the data inside of the would-be row and column values. And so you're thinking to yourself, where does this come in handy? And this comes in handy in cases where you are, again, storing multiple points of probe data, where you want to touch a point, store that point, move to the next point, touch a point, store the point, move to the next point. Because what you can do with these data arrays is not only can you store the values as numbers, but you could also interact with the data array via variable registers. So we could say def int rows and def int cols. And I can do something like for rows equals 0 to 19 and 4. And I can do another for cols equals 0 to 19. And then inside of that, do an N4 and put probe points, rows, cols equals 15. Make sure we space out our values here, our 0 to 19, and our cols equals 0 to 19. If I hit cycle start and I go to my offset page, you'll see that all of these points get populated to a value of 15. The reason for that is because of the for loop within the for loop. Again, if we look at this like an Excel spreadsheet, inside of our spreadsheet, again, we look at this as rows and columns. So we have all of our rows and all of our columns. The first for loop establishes the rows value of 0 as our initialized value for our counter, for our loop. So our rows is set to 0. It goes into the second for loop, which is columns, and that's equal to 0. But what it'll do is it will satisfy this for loop from the first value to the last value before it terminates the inner loop, goes to the N4 for the first loop, and then counts up. So looking at that, in this scenario here, if we go right into the for loop, it says rows is equal to 0. It dives into the second for loop. It says columns is equal to 0. So our probe point for rows and columns would be register 0, 0, which in our case in Excel is A1. And we'll say that that's 15. It then goes through every iteration of this inner for loop before it exits. So now it's stuck inside of here. So it'll then populate the remaining instances of 15. It'll end here. This for loop will count up to from 0 to 1. It'll then go into this for loop again, and it will run through all of the iterations of this for loop as rows 1, column 0, row 1, comma 1, row 1, comma 2, so on and so forth. So it does this. Once it satisfies the inner loop, it goes down to here. It counts up to 2. goes back into the inner for loop, starting at register 0, so rows 2, column 0. And again, it runs through the iterations of the inner loop before exiting, and then carries on through to 20 values. That's only one example, but I wanted to show that we can use rows and columns as a variable inside of our array structure, so we're not limited to numeric values for each of the data registers. We don't have to say probe points 0, comma 0 is equal to 12 and probe points 0, comma 1 is equal to 17, but we can do that. So even though I run through this 400 iteration loop, I then override those 2 points as 12 and 17 at the top of my variable list. But that's just me having fun. So let's do this a different way. I've defined a new variable called def real var1. Inside of the first for loop, I established that var1 is equal to 1. Inside of the second for loop, I say probe points, rows, and columns equals var1, and then underneath that, I do var1 equals var1 plus 1. So to show you how these for loops work with each other, if I cycle start and go to my offset page, we could see that here we have probe points 1, 2, 3, 4, 5, 6, 7, all the way up to 20. As it exits the inner for loop, it then resets back to 1, continues the count up to the next 20, and then just keeps repeating that over and over and over through all of the array values. Now keep in mind that this isn't something that you would do normally on a machine tool as far as doing these for loops within for loops, things like that. These are just examples to show you what can be done with these data arrays, and all we've done at the very top is only created a handful of variables. We didn't have to create 400 variables called probe point because that's handled by the array. That's handled by the dimensions of the array. Now the data arrays in the Siemens Sinumerik control will handle up to a 3-dimensional array, so I can put another comma 20 in there. Now I've gone from 400 to 8,000 arrays, and all I did was just add another section of data table. To show you that, I'll just M0 right here. So when I cycle start, I do have an alarm, but that is underneath. It already established the array for me, so I can look through here, and now we see that we have probe points 000, 001, 002, 003, and as we scroll down, you'll see that we just get larger and larger, and we still haven't even gotten, so we've gone through the 2-dimensional array, 20 and 20, and now we're on to the third dimension of the array. So where I'm at now is where we would have ended prior, and look where our cursor position's at on our scroll down menu. So we now have 8,000 points that are buried within this 3-dimensional array. Now 3-dimensional array, you can look at it in a couple of different ways. You can continue to look at it as an Excel spreadsheet, but you have that third dimension which kind of throws you off a little bit. You have to kind of look at it like a cube in a way, but don't let that detract you from attempting to use the arrays, because however way you can think of assigning these points is how you'd be able to utilize them in your program. So let's look at this in more of a real-world perspective. I have a def real probe 10, which will give me 10 probe positions in this variable array called probe. I define an integer called II, only because if you were to do a for loop in C language, typically you would say something like for int I equals 0, and then while I is less than 10, I plus plus to increment up. So this is a C for loop, and typically in for loops for C, again, they will use I for the first iteration, J for the second iteration, K for the third iteration. So in this case, I just declared an integer called II as my for loop counter for my probe array. I call up probe M6 position to where I want my start point to be. And then inside of the for loop, I have it coming down to absolute of Z 1 inch above my part. I come down at a feed rate of 10 inches a minute to Z minus 0.01. If this were actually a probing cycle, I would put something like mes equals 1 to define that I'm actually doing a measurement cycle. But I don't have probe trigger functionality inside of Sinutrain. The next line is going to capture that probe position in the data array value of II, which in the first iteration is 0, the second iteration would be 1, 2, 3, etc. I'm capturing current absolute position off of my work offset for Z. MM would be the measurement point, again if I were using mes, but in this case I'm just going to capture the absolute position off of my work coordinate. I then go back up to my Z 1 inch above, and I have an incremental move 2 inches across, so my endpoint would be an absolute position of 20 inches at the final point measurement. From there, I'll just say GO G90 Supa Z minus 0.1, and then we'll just end it out. But I'll put an M0 right there to show you my local variables, because I don't have a table built for this. But again, if we wanted to, we could always define a Gud table and have that to where it's non-volatile and it stores the information so that we can take it, extrapolate it, print it out as reports or what have you. So I'm just going to run this real quick. But what I'll do is I'm going to slow down my rapid and I'm going to slow down my feed a little bit. That way we can see as we go along inside of our local LUDs. If I single block into this program, you see that it initially creates the data array. It creates the II, which is our counter. And then as we go through, you'll see it captures first position. I'll take it off single block. And it goes through and it captures each position as it goes along the program. So I'll reset, watch our coordinate display, and you can see that it's cycling through the for loop, moves 2 inches, comes back around, measures, captures, back around, measures, captures, back around, and look at our X position. Every single time we do it, it moves, it moves, it moves. So once we have our probing routine, we can then take it, make it into a variable type program, and then build an easy screen for it. And if you checked out my playlist for that, I'm sure you could think of 1,000,001 ways to utilize both easy screens and arrays at this point to simplify your end user programming. It's a little bit of legwork in the beginning, but again, you can define as many variables as you need, want, or desire up to a certain point. You actually run out of memory as you're creating these variables. So at one point I was able to create an LUD with 10,000 points, but storing it as a GUD, I may be limited to say 5,000 points or something like that. So you do have to be careful when you're declaring your variables inside of your def tables, because like in this case here, I told this NCK real work offset, I told it 100, and this was going to coincide with the work offset table inside of here, but I ran out of memory and wasn't able to actually do that, and I wound up having to use 50 for some of my testing. As a quick point of reference, whenever you're creating these GUD tables, there's two different methods that you can use. If I go to def, go full screen, we can see that there's two different ranges that we can use inside of a def. NCK is an NC global user variable, and then chan would be a channel global user variable. So NCK can be used within any channel, and then chan would be channel specific. You can also use an option called pp stop for pre-processing stop. Instead of the stopre command, you can set it up as a default inside of here. You can set access rights for each of the variables that you're using. And again, you have your data types, physical units, limit values. So you can set limit values for your variables, and then name would be the name of your variable. Inside of here would be value 1, value 2, value 3, which is if you were defining an array. Again, you would say square bracket value 1, comma, value 2, comma, value 3. Gives you a three-dimensional array. If you look up arrays inside of the Siemens help file, at the bottom, it actually shows you your initialization table, kind of like how I showed with the Excel spreadsheet. I went back into my UGood definition file, and I commented out a lot of stuff that I'm not really using in my next example. So if I go to my offset page and I go to my UGoods, we can see right here I have a list of probe point 00 through 15. Again, Excel spreadsheet. If we're looking at probe point, we can even do it where we have probe point here, and we can start our table here at register 00, 01, 02, 03, 04, 05. And then here we have 10, 11, 12, 13, 14, and 15. I could even take these and move them over one spot and say that this row and column holds this value of, say, 1.1, 1.125, 1.132, 1.156, 1.143, and 1.178. Makes it a little clearer. On the opposite side here, we have our other registers, and we could say 1.3, 1.32, 1.34, 1.355, 1.387, and 1.3627, whatever. So this gives you an idea of what these probe points are doing. These are capturing, in this case here, z-values of each of these point iterations. Or in the case of this, it's capturing x and y values. It's just a practice example. So point 00, 02, and 04 are capturing x values, and 01, 03, and 05 are capturing y values for both 0 register and 1 register. If I transpose some of that information to here and I say 1.3, 1.321, 1.356, 1.348, 1.395, and 1.374, and then get into the second area here, 1.3158, 1.3156, 1.3142, 1.3167, and 1.3, I don't know, 1.31985.4. So again, x value, x value, x value, y value, y value, y value. Think of it as we are probing two faces that are parallel to each other. We want to get the minimum and the maximum probed points in x and y. You would do it in z, but just for example. If I go into my program manager and I go to this program here, That's essentially what this is doing. This is defining integers for count and index. It's creating an array count of 6. It's using all of these variables to establish the data points inside of these arrays. So index position 0 and index position 1, and then our count goes from 0 to array count, which is right now a maximum of 6. So this is a little long-winded. I could do this with a for loop, but because I'm doing the situation where every other data point gets an x value and every other data point gets a y value, I'm doing some funky math here with while loops instead of for, and at the end I'm counting my count equals count plus 2 instead of the for loop counting up 1 per cycle. The while loop we can manipulate to count up as many register points as needed. So I'm establishing the array of min point, index, position 0 to 9999, and min point, index, count position 1 to 9999. We then go into the while loop, and while count, which is now currently 0, is less than array count, which is 6, it will go in and it will cycle through all of this here. And as it's going through the while loop, the if conditionals are checking to see if probe point, index, and count is less than minimum point, index, comma 0, which is this one here. If index, comma 0 is greater than probe point, index, count, it will then reestablish min point as index, comma 0 to the probe point, index, comma count. And then it'll output a string under min underscore x underscore side underscore a equals, and it'll say point, it'll concatenate the index, it'll add a comma, and concatenate the variable count. It'll do the same thing for the maximum values for x. It will increase the count number to 1, so the second value in the data register to a 1, reset the index back to 0, and then go in to this while loop and do the same thing for minimum y side a and maximum y side a, and it'll write the values into the strings using the concatenation right here to add the comma and the word point. So it'll add point, concatenate, index, concatenate, comma, concatenate, count. It's easier if I show you this as a running program. So I'll execute this. So it runs through. All I did was fill in the probe points from 0, 0 to 1, 5. The rest of the stuff is handled by the while loops and the if conditionals, tying back to the values inside of these probe points. It gives me my minimum points for, say, side 0 x, side 0 y, and then side 1 x, side 1 y. And then it gives me maximum points for those 4 as well. It then tells me down here inside of these strings that the minimum x for side A is 0.00, the minimum y of side A is 0.01, the maximum side A in x is 0.04, and maximum y of side A is 0.05. So if we were to look at these values here, we would see that first value, third value, and fifth value, the minimum point is register 0, 0. And in the case of 1, so 0, 1, so second value, fourth value, and sixth value, yeah, the lowest point is 0, 1. So right here, right here. So I hope this gives you a little bit of insight as to how helpful the arrays can be in the Sinumerik control. It's something that when I discovered the control was able to do, I was beside myself, so to speak, because I'm used to coming from a world where everything has to be done with pound 1 or pound 2 or pound 100, pound 500, something like that. And even with those, you're only limited to a certain amount of variables that you can assign. And then there's times where I've had to use pound and then in square brackets pound1, something like that, where I would say pound1 is equal to 0, and then pound1 is the actual output value. So pound0 would be null, pound1 would be pound1, pound2 would be, so on and so forth. So the ability to have arrays is nice because you don't have to do any of the funky manipulations to your variables. All you're doing is just incrementing up through a data register in your array. And again, you have access to 3 dimensions of that array, so you can use that to store millions and millions of points, and you would just access it through the data table. So that'll pretty much conclude what I wanted to show you on data arrays. I hope this was helpful. I hope it wasn't overly confusing. I hope it wasn't daunting in any way. I know it is a little scary to see this and see what it's capable of, and getting into it, trying to explain it in a way where my examples are kind of in depth, but showing it in a way where we can use it for a simple point capture routine and then extrapolate that data later on in our program to find the average or to find the minimum point, the maximum point. There's a bunch of different ways we can utilize that. There's these min val, max val commands that we can use to find minimum values of variables, maximum values of variables. You can use a for loop inside of this to capture that. You don't have to use all the funky stuff that I did. So there's many ways to skin a cat, and the most useful method of doing it is to create these data arrays, because now you're storing those values in a known variable with their own specific point of data, if that makes any sense to you. So thank you all for watching. Please be sure to like and subscribe if you're enjoying the content. It's really really important, and it's very helpful. It keeps me motivated to make more videos. And drop a comment in the section below. Let me know if there's anything that you would like to see as far as the Siemens control goes, or as far as Linux CNC goes. I do plan on making tutorial videos on O-code logic inside of Linux CNC, which is very similar to macro B, if you're familiar with that. Similar in concept to this stuff here. If conditionals, while loops, math, things like that. Thank you so much for watching, and hope to see you soon.